Okay, so now we want to talk about how to make alcohols, right? And I have good news for you here. Everything that you're going to hear in this section is review, 100% of it. So we are preparing alcohols. First of all, let's talk about how we did it in Chapter 7. In Chapter 7, we took alkyl halides, and we made alcohols, right? And we did it via Sn1 and Sn2 reactions. So let's review those reactions and we'll look at the mechanisms as well. So first of all, we did this with Sn2 mechanisms by taking hydroxide, right? Okay, can you read my writing? Taking hydroxide, this is just a speculator ion, right? So we took hydroxide and we took these electrons, came in, backside attack. Uh-oh. What happened? Backside attack. And sorry, I'm not sure what's going on there. Backside attack and the leaving group, which I might have called LG. What's going on here with my pen? LG left, right? The nucleophile came in and the leaving group left, right? And that was done in a concerted fashion such that the rate of the reaction was dependent both on the substrate plus the nucleophile, or not plus, and the nucleophile, right? That was a Sn2 reaction. It was bimolecular. Now, Sn1 reaction, which was unimolecular. Can you read my writing? Unimolecular, that is the rate was just dependent on the substrate, right? That happened like this. First of all, the leaving group left. So you have to have a good leaving group. And when the leaving group leaves, I don't have a lot of space here, so I'm going to go real kind of small. That's a carbocation there. A little ugly. Carbocation, the leaving group leaves, and when the leaving group leaves, the water molecule comes in either side, right? So you get racemization. Comes in both sides, actually, right? Half of them will come in this way, and the other half will come that way. Right? And then you get a base that comes and takes that proton and leaves this guy, right? Okay, so this was an Sn1 reaction, and it was unimolecular where the rate was dependent only on the substrate. So this was relatively slow. Why was this relatively slow? It was relatively slow because the leaving group leaves on its own. It's not pushed off. And it leaves behind a carbocation, which is, in terms of activation energies, relatively high, right? Because it's not as stable as a neutral compound. So this was relatively slow, and it uses a weak nucleophile, which we, in this case, showed was H2O. All right? So why isn't a stronger nucleophile, such as hydroxide, used under Sn1 conditions? Oh, wait, that's Chapter 7. Consider going back and looking at that. Look at the section on nucleophiles in Chapter 7. There's a whole section on it. Well, I mean, there's a whole set of paragraphs within a section on nucleophiles there. Go back and look at that. Why isn't a stronger nucleophile used under Sn1 conditions? Okay, so we got alcohols. We made alcohols by Sn2 or Sn1 reactions from alkyl halides, right? We also got them from alkenes. And these were addition reactions, right? This is Chapter 9. Okay, so in one case, we used simply dilute sulfuric acid. Okay, this was subject to rearrangement because it made a carbocation intermediate. Then if we did not want rearrangement, we used mercury 2 acetate, right? I'm afraid to say that. I think I got it wrong. I always forget the name of this thing right here. Okay, we use that. I think it's mercury 2 acetate. So in water, and that gave us sort of a weird intermediate, but was not a carbocation. Okay, and then we chased it with sodium borohydride. 2 steps. 1, 2. Right, and that was oxymercuration, demercuration. That was in section 9.5. Go back and review that. And then finally, if you wanted an anti-Markovnikov addition, then you used BH3, that's borane and THF, right? And you chase that with hydrogen peroxide and hydroxide. Okay, 2 steps, right? This is only 1 step. These 2 down here, 2 steps. Okay, so we did this with both with SN1, SN2, and also with addition reactions. SN1, SN2 was chapter 7. In chapter 9, we did addition reactions from alkenes.